Welcome to Operating Systems Unit 9 on Process Synchronizations. This is video 1. Today we're going to talk about a software solution to the critical section problem called semaphores. So semaphores are a software solution that use atomic methods in order to control access to the critical section. So an atomic method just means that it is a set of instructions that are treated as if they're one instruction. And there are 3 operations that semaphores do. It's just a global variable, and these operations are part of the code in controlling the critical section of the multiple processes. The number of processes that share a semaphore it doesn't matter. There's not a limit on it. It's just the way the semaphore is used. So there are 3 operations. The first is initialization, there's wait, and there's signal. So the wait operation looks like this. The wait means that usually it would be in the entry code of the processes before the critical data is accessed, and all the processes would run their wait. So if the semaphore was initialized, say, to 1, and all the processes ran their wait, the first one that ran its wait would be the one that would hold and own the critical section, because if you take a look at this, it says while s is less than or equal to 0, then you must wait and you cannot move. But if s happened to be 1, then this process would be the one that would decrement the s and change it to 0. So it would then own the lock. So I'm going to go over an example in a minute. I'm just giving you an overview right now. And then after the semaphore is released, or when the critical data becomes available, the other operation is called a signal, and all signal does is increment. It increments it back up again. So you can see if you have errant signals and a global variable, you may have issues with controlling access to the critical data, because all a signal does here is change the value of the global variable. And there are different types of semaphores. There are binary semaphores and counting semaphores. A binary semaphore means that the semaphore can only have 2 values, 0 and 1. And a counting semaphore means a semaphore can have multiple values. And then there are standard semaphores like this, in which while the processes wait, they basically sit there checking the semaphore and checking using CPU cycles in order to check, which is called busy waiting. And then there's complex semaphores, which have processes they're waiting. And that's what this is. This is a complex semaphore, so we'll assume that the semaphore is initialized to 1. And this is a binary semaphore, so it has only 2 values, 0 and 1. So the wait operation is like this. If the semaphore is 0, that means that either the critical data is not ready or another process is inside the critical section. Then this process is going to have to block itself and wait. Otherwise, if the semaphore value happens to be 1, remember a binary semaphore can only be 0 or 1, then this process will decrement the semaphore and then go into the critical section. And then when it's done, if the semaphore is 0 and there's a process waiting, rather than changing the value back to 1 and having the other ones check, it's just going to wake up the next one is going to get notified and get woken up, the one that's in the front of the queue. This is another example of a different queue that's in the system, a queue for synchronization. And if there is no process waiting, then this process, when it exits, it will just increment. So let's just review. A semaphore is a global variable that has 3 operations: initialization, wait, and signal. Semaphores can either be binary or counting. A binary semaphore has 2 values, 0 and 1. A counting semaphore can have any numerical value. The types of semaphores, you can have a standard semaphore like the first one I showed you, where the wait just does no operation if it's less than or equal to 0, and decrements if it is greater than 0. And that's a binary semaphore. Or a standard semaphore could also be a counting semaphore. And then the second example we looked at, where the process would block while waiting, is called a complex semaphore. And that could either be binary, meaning the global variable could have the values 0 and 1, or it could be counting. Now we're just going to do a little example here. Pretend that you're at a doctor's office, and the way that there's no receptionist, so the way to control access to the doctor's office is by a number on the door of the doctor's office. So when you arrive in the doctor's office, say for example, the first one to arrive would be the doctor, and the doctor, if you were to arrive and there's a 0 on the door, that would mean to you either that someone is in there with the doctor or that the doctor has not arrived yet. So the doctor is going to arrive and the doctor is going to signal and change it to a 1, which if you take a look at the wait, that means that if I arrive and I see a 1 on the door, that means that the doctor is going to be in there and ready and waiting for a patient to arrive. So there's a 1 on the door, and patient N is going to arrive and run the wait. So here comes patient N, sees that there's a 1 in the door, changes the 1 to a 0, and is in there now with the doctor. So patient N is in there with the doctor, and there's a 0 on the door because that indicates that the doctor is busy and not available, and patient N is in the critical using the critical data, which is the doctor. Now another process, P1 arrives and checks the wait, and P1 is not able to go in. P3 arrives and checks the wait, and P2 arrives, and these are busy waiting. They're just cycling around and they just keep checking their wait, checking their wait, checking their wait, until eventually PN finishes, runs the signal, changes the value to 1, and now P1 will run the wait, and then P1 will then be in there with the doctor, and any other processes that come along will also have to wait. So that's just a scenario of a basic standard semaphore, but using this numerical value on the door of the doctor's office. So now we're going to move on to the same scenario, only with a complex semaphore. So there's a 0 on the door. The doctor arrives, puts the signal, and now the doctor is in there and ready to see any patients that are going to arrive. So PN arrives, runs the wait, goes here. If S is equal to 0, I block and queue. If it's not equal to 0, I'm going to decrement. So the patient here is going to decrement it to 0 and will be in there with the doctor. So now PN is in there with the doctor, and there's a 0 on the door, which indicates that the doctor is busy and not available. So P1 will come along, run the wait, and we'll notice that P1 needs to block and queue. P3 comes along, P3 needs to block and queue. P2 comes along, P2 needs to block and queue. So they're all there on the couch in the order in which they arrived, or maybe the receptionist put them in an order, and they are blocking and waiting to see the doctor. So if you take a look now, this 1 on the end here, when PN is finished, PN is going to signal. So take a look on the right end here where the red arrow is pointing. Instead of PN changing the value from a 0 to a 1, PN is going to come out and wake up this one who's in the front of the queue and allow her to go in to see the doctor. So now she's in there with the doctor, and the 0 is still on the door. So when P1 finishes, she will go out and wake up the next person, and they will go in, and so on until eventually the last patient is finished with the doctor, and we'll change it to a 1, in which case the doctor would be sitting in there and waiting for the next patient to arrive. So here's an example of a counting semaphore, and I'm going to record this, make an animation out of this counting semaphore example, and that will be part 2. So thank you very much. In the next video, I will do the example of the counting semaphore.